to talk about the issues that you face putting those SoCs together. What are the challenges in integrating high-speed serial interconnects to an SoC?
I think that is part of the presentation as I explained, but the one of the aspects that that I would like to address that we have not addressed so far is in terms of the process. And as the process is migrating from 45, 28, now making the IP available in each node for that particular process. And as you know, the process also keeps changing, the node keep changing. So the analog and the mixed signal aspects that I did not address in my part. Now I would like to, along with all the things that I mentioned, I would like to add the complexity of the process and the complexity of the DFM, DFT, all those aspects. And to get the interface working at now at USB 3 we are talking about 5 gigabit per second, and it is going to maybe 10, and it's going into the post 10 numbers. Now this is going to be a key challenge for all of you SoC designers to get it working. So the analog IP, the controller IP, the verification IP, and the software all working together and be compliant. And this is one thing I consider as an important challenge.
I would say with respect to interfacing the high-speed serial I/O to the on-chip interconnect, particularly using a standardized interface such as AXI, that perhaps that is not the major challenge in the SoC. If you consider the raw bandwidth in the DRAM subsystem compared to the high-speed serial, it's still maybe an order of magnitude higher, and at the same time the contention for the DRAM channel is usually considerably higher than it is for the high-speed serial as well. So I think it's important to keep in perspective high-speed off-chip communication in terms of bandwidth is still a lot less than the interface to DRAM.
Yeah, so basically in all these integration, we've heard about Ravi actually explaining, bridging a link with what has been disclosed this morning, is that all these high SerDes medium of communication, whether they are off-chip or on-chip, now start to be actually quite complex piece of IP. That's why when you go and address some company, as the three of us are here, we are specialists in our technology. That's why whenever you go and get your IP from outside for the off-chip or on-chip interconnect, what you benefit of is full team of engineering, pre-verified IP, tested everything. To go back to this parallelization of your tasks. Like that you can focus on your architecture of your SoC and get pre-verified working third-party IPs.
So software development, and especially verification, as you all know, and mass costs are usually quoted as the highest cost factors in developing an SoC. So the question is, can approaches to on-chip and off-chip communication contribute to reducing these cost factors? I'll let you start, James. What was your question?
I think certainly with regards to mask costs, the cost of a mask is what the cost of a mask is. Where the saving may come from is being able to tape out silicon right first time and not having to go through a second spin. I think being able to verify your design very well prior to taping out is critical. I mean, that's obvious to get silicon right first time. Most of the potential errors in new architectures being taped out in an SoC typically do occur in the area of the interconnect or interfacing to the cores. So the approach of using verification IP to verify that each of the core interfaces has been fully verified, as well as selecting an interconnect technology that itself has been fully verified, even though its particular configuration may be unique, I think is probably the best way to contribute to reducing mask costs. With regards to software development, I think having fast models of the entire system, and today I think the best answer there is indeed cycle accurate system C models, is probably the best way to give the software guys a handle. I'm not talking about application software. I'm talking about the guys who are trying to model the video algorithms as it interacts with memory, where cycle accuracy is important. If you can do that before taping out your chip, or doing full chip RTL integration, I think that's valuable.
And what we heard in this regard is, then we're here talking to you, hey, our IP works, it's pre-verified, and then we got most of the time the comment from the customer say, yes, fine, but how do I differentiate myself, right? If my competition is going to buy the same IP, how do I make sure that my product is going to work better than his product? How the differentiation comes from now if everybody goes and pick up the same IPs? Well, you can look at the house of your neighbor. You buy the same bricks, same piece of wood, and some people will build castle, and some people will build just crappy little houses. So basically, the differentiation comes from somewhere else. Differentiation comes from your methodology, your team, and how your team will take benefits of these already pre-verified available IPs. And this is what I think is actually one of these most important things for SoC. SoC, next thing you heard about is integration. And actually, the integration process, the one you're coming up with, this is what will make you differentiate yourself from the competition, from a time to market point of view and from an SoC cost implementation point of view.
Market adoption of packet-based network-on-chip interconnect is something that we've been talking about, and the question is it myth or reality?
I believe the technology does have its place. However, the cost of running the address data over the same wires as the payload data, which is essentially what a serialized network is, does have a penalty in terms of latency. And while in certain kinds of devices that trade-off can be acceptable, I think in most devices that people are developing today, latency is still perhaps the most critical, and therefore keeping the address and data on separate wires and not incurring extra penalties is still the right choice for most SoC designs today. Looking to the future, at most advanced process nodes and doing some of the connection at the top level, sometimes indeed where latency is not as critical as it would be in, for example, the CPU to memory path, the serialized packetized link technology does have a place, and indeed Sonix is also implementing that as part of the total solution. But as I emphasize, today for the latency tolerant systems that I think most people are developing, I think the time for this serialized packetized technology is not yet just now. We're not in 28 nanometer and 22 nanometer for the most part just yet.
So I'll have to comment that one. If you make this comment, it's because you might not know what we're doing, so maybe your implementation cost latency to people. Arteris came with their second generation of interconnect, and this latency story is long time gone. We have small design in pretty much every market, and actually we have an implementation of packet-based interconnect that doesn't cost any latency at all. Basically, the concept here is that if you have some CPU to DRAM paths that are actually latency critical, we have actually ways to do all these things behave as if it was a normal address and data parallel system. So actually the latest, that's why I was explaining earlier that, yeah, the first generation of interconnect were addressed to more complex chip. So that was true until 2009. But now with our second generation, actually, we've been able to scale it down and solve this latency concern, which just doesn't exist anymore.
Mike, I should have been sitting between these two gentlemen. So, yeah, I would like to make a general observation on this technology adoption, because I've seen, when I started the semiconductor, everybody is doing with schematics, and how they moved to Verilog and VHDL and so on, and what it took. Typically, the new designers who came in, they were software savvy, and they knew Verilog, and they got much better, much quicker. They adopted this new technology. Now, I saw the same thing in high-level design. If you look at the C-based design and so on, for 10 years, there are a lot of people have talked about this, but it never became reality for whatever reason, because adoption is, everybody has a comfort zone, and people tend to to get into that comfort zone unless there is a real push from the management, there is a real requirement. And what I am observing is the last few years, if you look at, again, why companies are talking about profits, because it's a very, very tough environment out there. It is not those times where everything is growing, everything is rosy, everybody is making profit. Here, only the tough will survive. And very important that management has already looked at every aspect to reduce cost. Now they are looking at how can I improve productivity. I cannot cut any more engineers, but now we have to improve productivity. And I think all the technology that we are talking about, one has to look from improving productivity. And now I know companies, very large corporations, they are invested huge amounts of money in terms of Verilog based verification. Now they are insisting that they move to object oriented or system Verilog environment. And tons of money has been, and ecosystems we created, throwing out, because they know that's not the right thing to do. The move on to the new technology is very important. So I am seeing that with this tough environment out there, the semiconductor business, the manufacturing and all that, improving productivity comes by adopting newer technologies. And those customers and those engineers adopt these kind of technologies, you can sustain for longer, you can make more profit quicker. Otherwise, like we heard, if you only keep all the old technology, that you will, that's why people call dinosaurs, right? So some people disappear because they cannot adopt fast enough.
We've been talking about network on-chip interconnect, high-speed interfaces, the complexity that's happening in the SoC space today. And one of the reasons that complexity is happening is because it can. So on May 7th, 1997, you all know what happened that day, right? This was 13 years ago. Intel introduced the Pentium 2 at 233 megahertz. Now that puts everything in perspective. That was 13 years ago, Pentium 2. A Pentium 2 is not even usable today. You cannot run today's operating systems with a Pentium 2. That's just 13 years ago. You can see how fast the pace of change is happening. The cell phone that most of you have in your pocket has a processor in it that's more sophisticated than that Pentium 2. In fact, it probably has 4 or 5 processors in it that are more sophisticated than that Pentium 2. And that requires sophisticated networks and sophisticated on-chip, off-chip communication capabilities just to keep up with the infrastructure. And think what this is going to look like in the next 5 years or 10 years or, for that matter, 13 years. How fast the pace of change is going to happen in the SoC world as we move down to deeper and deeper sub-micron technologies. So with that, I'd like to thank the panelists, Ravi, James, and Xavier. If you'd thank them, please.
Thank you. Thank you.